Avocoder. In this lesson, we're going to dig into the history of object-oriented programming, how it has evolved, and why this paradigm was acknowledged by many experts as the best paradigm to describe the world around us. Let's begin. Long time ago, in a galaxy far, far away. Alright, computers were not invented that long ago, but back then they were nothing like this sleek machine in front of you, and despite their size, they were mostly used for computations, or they could only follow a simple sequence of steps or algorithms. To illustrate what I mean, let's imagine a breakfast preparation process. Step A, prepare the ingredients. Step B, put the pan on the hob. Step C, ignite the hob. Step D, mix the ingredients, and so forth. We humans normally follow these algorithms ourselves in real life. Therefore, this is one of our approaches to describe the world around us. So the first programs were imitating this. Take data from here, put it there, then do something with this data and move this data further. However, even in real life, and especially in real life, events tend not to happen as they were planned. For instance, what if an ingredient for our breakfast is missing? In that case, we'll probably have to go to the shop, or call a delivery, or book it online. So imagine we chose to go to the shop. There things could get even more complicated. What if there is no stock? Or what if they only have a brand which we don't fancy? Or what if they don't have a pack of our usual size? Should we take a couple smaller ones, or keep our own stock and buy the bigger one, or possibly check out another shop nearby? Imagine that we would have to design an algorithm to accommodate each possible case. An epic spaghetti code with numerous forks and thousands of conditional statements for cases when there is a slightest change in the flow of events could possibly be seen from space. So the next approach was the procedural one, where the repeating steps were formed into blocks called differently in various languages, for example, functions, subprograms, procedures, etc. The general idea was that they could be called when required and reused as many times as required. But this approach had its own flaws. Let's get back to where we left off. We couldn't find the right ingredient in our local store, so we would probably need to head to a shop nearby. But how would we implement this programmatically? Write another procedure? And what if we'll meet someone in that shop? Ignore that person because we don't have a procedure to handle this event? How can we make sure that we are ready for all possible scenarios? We might end up with a massive stock of procedures that might never be used, but we will keep them just in case. This approach might turn our program into a bloated monster with only a tiny functional part, and the rest will just be a dead code. The object-oriented approach, in essence, was designed with a simple thought in mind, that everything around us is an object. And it seems natural for us, humans. We live in a world full of objects, we interact with them, and we are objects ourselves. And so this concept comes natural to us already. For example, here is a dog. It has certain characteristics: color, height, weight, and age. It can do certain things like stare, hide, or munch. And we can interact with it as well, like call it or pet it. Software objects also can have characteristics or state, and a behavior or methods. When we say that an object is in a certain state, it means that all of its properties are defined by a set of certain values. They can be defined either explicitly or by some default settings. The object's behavior is defined by the object's methods. Put it simply, all possible options of interaction with the object, or how the object reacts to those interactions, or ways it can interact with other objects. So in generic terms, objects' methods can potentially change the object's state, and the object-to-object communication is generally done via methods. The next important concept we need to look at is a class, which serves as a blueprint that defines the variables and the methods common to all objects of a certain kind. When we create an instance of a class, the system allocates enough memory for the object and all its instance variables. The class dog has instance variables that describe its state and methods that describe its behavior. And if we decide to instantiate that class, or in other words, create a particular dog based on this description, we could simply do it like this: dog Angela equals new dog, where dog is a type of an object which we instantiate using the dog class as a blueprint. Angela is dog's name, and keyword new means that we're creating a new object of that class. And if we would want our Angela to be a young Labrador, we would instantiate the variables responsible for Angela's state like this: string breed equals Labrador, int age equals 2, string color equals beige. Of course, this lesson was just a humble introduction to object-oriented paradigm, and we're going to learn so much more later on this course. Things like polymorphism, inheritance, encapsulation are among those most popular topics for Java interviews across the world. And by the end of this course, I will make sure that you have a firm grip of all these concepts. So please give this video an Emperor's thumbs up, toll the bell and subscribe. That was V, thank you and goodbye.